Hello. So we have now talked about solutions, solute, solvent, all those kind of things, a little bit about how things dissolved. And what we're going to get into now is some of the language that we use to talk about solutions and what's dissolved in them, and also some of the math of it, which I know is your favorite part. So what kind of things are we going to talk about? First, we want to talk about solubility in general. What kind of things we mean when we talk about soluble? Well, it turns out that just because something's soluble, it doesn't mean you know everything there is to know about it. Salt is soluble in water, but I can take a little teaspoon of salt or a little pinch of salt and dissolve it in water, or I could take a tablespoon of salt and dissolve it in that same amount of water, both of which will dissolve, but there'll be different solutions, won't they? One will be a lot saltier than the other one. And so we haven't actually explored everything there is to know about solubility just by saying, hey, it's soluble. So we're going to introduce some language first about what are called saturated, unsaturated, and supersaturated solutions, and then go into some of the math behind some of those. So let's go with the definitions first. What is a saturated solution? And a saturated solution is one in which, oops, don't know what happened there, a solution, and some people abbreviate solution SOLN to save a little bit of writing, where no more solute can dissolve. For example, if I take myself a beaker of water and I just start pouring in salt, and I get to the point where I put in so much salt that there's this giant pile of salt at the bottom, and there's some very salty water up on top, but there's a huge amount of salt. No matter how much I stir and stir and stir and stir and stir and stir and stir, that salt is never going to dissolve, right? There's a limit to how much that can dissolve. In fact, that limit, if you want to know a number, is about 35.9 grams of salt for every 100 grams of water. And that 35.9 for 100 grams is actually what we call the solubility of salt in water. We say that we can dissolve up to 35.9 grams of salt for every 100 grams of water. But if we put in, into 100 grams of water, we put in 500 grams of salt, not all of it's going to dissolve. And then if we put in one more gram, is that gram going to dissolve? And the answer is no, because we already dissolved as much salt as can be dissolved. Nothing more is going to dissolve. And that's what we mean by a saturated solution, is that no matter what we do, we keep putting in salt. Just because we keep putting in salt doesn't mean more is going to dissolve, because the solution has taken as much as it can. Now, in fact, we can actually get right to that limit. We can put into 100 grams of water 35.9 grams of salt, and we would also have a saturated solution, because if we took one more little salt crystal and tried to dissolve that in, the solution would be like, well, I'm full. I can't take any more salt. That salt would just sink to the bottom and would just be a little salt crystal down on the bottom. And that's what we mean by a saturated solution. Even if I had the tiniest little crystal, it's not going to dissolve because no more can dissolve. Now, if that's what a saturated solution is, you can probably guess what an unsaturated solution is, and it's the opposite. An unsaturated solution is one where more solute can dissolve. So an example would be if I took my water, I had a big beaker of water, I put 2 salt crystals in, I put them in there, I stir it up, those salt crystals dissolve, I don't have the crystals anymore, I just have slightly salty water, a little tiny salty. If I tried to put another crystal of salt in there, would it dissolve? And of course it would, right? You can handle a lot more salt than just a few little crystals in some water. And so that one would dissolve, which means that our solution was unsaturated. We can dissolve more salt in it than we have. So a saturated solution, one where you can't dissolve anymore. An unsaturated one where you can dissolve more. Now, what about the last thing which called it supersaturated? No, not supersaturated. Supersaturated. It's one where you have dissolved more solute than possible. And that sounds really weird. Like, wait, what do you mean I dissolved more than possible? That's not possible, because otherwise it would be possible. So does a supersaturated solution exist? And it does. I'm going to caution you that a lot of things you're going to see out there when they talk about supersaturated solution. Let's go up here. And they're going to use language like, oh, if I take 100 grams of water and I add 40 grams of salt, what kind of solution do I have? And they're going to look for the answer supersaturated, because you're like, well, I added more salt than is possible. But I like to not do things quite that way, because what really happens is if you take 100 grams of water and you add 40 grams of salt, 35.9 grams of those dissolves, but 4.1 grams just sinks to the bottom, and you have a saturated solution with 4.1 grams of salt sitting at the bottom. You don't end up with a supersaturated solution. But even the homework system that we use in this class does expect that. Expects that when you talk, oh, I put in 40 grams, that you're going to tell it, oh, we have a supersaturated solution. So you need to be aware of that some people use the language that way. But it turns out it's actually really hard to make a supersaturated solution. In a little while, we're going to talk about what happens to solubility with temperature. And for most things, as you increase the temperature, the solubility goes up. So sugar, for example, at room temperature, it's 100 grams of sugar for every, 200 grams of sugar for every 100 gram of water. But as you increase the temperature, it goes up by a lot. So you can take 300 grams of sugar, put it into 100 grams of water, you heat it up, eventually that sugar will dissolve. And if you're very, very careful, you can cool it down, and that sugar won't come out as a solid for a little while. Eventually it will, because it's actually unstable. But for a moment, you can end up with a supersaturated solution. If you've ever made rock candy at home, you probably heated up a lot of sugar and water, made a supersaturated solution, and then slowly let it cool down and let those crystals form. That's what you were doing. So a supersaturated solution, very difficult to make. You actually have to try to make them by heating things up, dissolving more than possible, cooling it down carefully. So you don't run across them all that often. But there is one supersaturated solution that you run across probably regularly, and you don't even know it. What happens when you leave honey sitting on the shelf for too long? Well, eventually it crystallizes. And the reason it crystallizes is because honey is actually a supersaturated solution of sugar in water. And eventually the sugar comes out. But it's amazing to me that the bees make supersaturated solutions. Like, wow, that's pretty cool. How do they do that? I actually don't know how they do that. It's really neat. So that's a supersaturated solution, one in which you've dissolved more than is possible. They can be made, but they're hard to make. We're not going to pay too much attention to them, but I wanted to point them out in case you saw them on the homework or in other places. We're going to mainly focus on saturated and unsaturated solutions. And what we're going to look at next is how can we calculate that? How can we determine mathematically and precisely whether a solution is saturated or unsaturated? Because let's say you have a medicine and you're giving a patient a certain amount of it. If you're getting towards the solubility limit of that medicine, you might not be able to add more without having some bad side effects like the medicine crystallizing in their bloodstream. You don't want that. And so we have to know a little bit about how to figure out solubilities. And that is what we will do next. So we're going to do a few examples, because examples are always the easiest way to learn something. And we're going to determine whether something's saturated or unsaturated. I'm going to show you a couple different ways of calculating it, and either way you calculate it is just fine. So the first one we could probably do just by looking at it and thinking about it. We've got a situation where we take 160 grams of potassium iodide added to 100 grams of water at 20 degrees Celsius. And I'm going to give you some information that says the solubility of potassium iodide is 140 grams for every 100 grams of water at 20 degrees Celsius. So you're like, well, added more than the solubility, and so it's probably saturated. And you'd be absolutely correct. But let's go ahead and find a quantitative way of doing that for when the numbers aren't so easy to just glance at. And it turns out you can start with pretty much any of the given quantities that you want. But usually you don't start with the solubility because it's got a fractional unit. You start with one of your other units, which is either the solute or the solvent. Let's go ahead and start with the solute in this case. We've got 160 grams of potassium iodide. And what we're trying to find out then is how much water do we need in order to dissolve that much potassium iodide? So we're going to look for grams of water. We're going to set up our conversion, and just like every other conversion we've done in this class, we cancel out the unit we don't want, and we put the unit that we do want. This guy cancels, we get the unit we want. Then we figure out the numbers. Units first, then numbers. Now, if you remember in the last chapter, I said, well, when you're using the periodic table and balancing reactions, you can't go in one step from grams of one thing to grams of another thing. You just can't do that. Right here, I'm going to give you an example where I go from grams of one thing to grams of another thing in one step. And to some people, it's like, hey, don't be mean to us. Don't tell us things and then untell us things. But if you listen carefully, I said with balanced reactions, you can't go from grams of one thing to grams of another thing in one step, and you can't with a balanced reaction. But with solubility, you can. If you're given solubility information in grams of one thing to grams of another thing, by all means go from grams to grams in one step. So we look down here and we have to figure out what numbers to put in here. Grams of water to grams of potassium iodide. That's usually going to be a solubility. How do we know what number goes where? Numbers stay attached to their units. 140 is attached to grams of potassium iodide, so it goes on the bottom. The 100 is attached to grams of water, so it goes on the top. I type this in my calculator just as 160 times 100 divided by 140, and I get myself 114.2857. I got 2 sig figs here, so I'm going to give myself 2 sig figs at the end, 110 grams of water. So what does that tell me? What this tells me is that in order to dissolve 160 grams of potassium iodide, I need 110 grams of water. And this is one of those cases where the calculation actually isn't your answer, because I'm trying to determine whether it's saturated or not. So I have to go one step further. I have to add the following, is I have 100 grams of water, because that was given to me up in my problem statement up here. If I circle it again, it was given to me that I have 100 grams of water. That's not enough. All my potassium iodide will not dissolve. And if all of it doesn't dissolve, it means I can't dissolve anymore, and we call that a saturated solution. Now, here's a hint. If on a quiz or test you've got an upload problem and it's asking about the saturated, unsaturated stuff, I need you to say those things. I need you to have sentences that look something like that. They don't have to be those exact words, but that tell me the logic that got you from the calculation to your answer. If you just say 110 grams of H2O saturated, I won't give you the full points. I need that logic in there so I understand that you really understand what you just calculated. Okay, so that's a hint that maybe that might be coming up, somewhere in an exam that you might have to upload some work for. Just saying. All right, so that's one way of doing it. Turns out we could have also started with the 100 grams of water, and I'll do that in the next problem. I won't belabor the point here, but I'll do that in the next problem and show you that you can solve this problem in 2 different ways, and you get kind of the same end answer, but your logic is slightly different. So let's do another one. We've got 8.0 grams of lithium hydroxide. We're going to add that to 50 grams of water. The solubility is 12.9 grams for every 100 grams. And, some of you might still be able to do this one in your head. You're like, 50 is a half of that. I double that. Okay. But, the numbers can get a little more complicated than that. So let's figure out how we can calculate it. Last time we started with the solute, the lithium hydroxide. This time let's start with the water. I've got 50 grams of H2O, and what I'm trying to figure out is grams of lithium hydroxide. If you notice, those are the only units I have. I've got grams of water and grams of lithium hydroxide in all my units. So I know it's going to be some combination of those. As with all things, units first, grams of water on the bottom cancel out there, grams of lithium hydroxide on the top. Now we figure out numbers. What's our ratio? Grams of lithium hydroxide to grams of water. When you see grams of something and grams of something, you're talking about a solubility. If we've got solubility problem, great. If you don't have a solubility problem, maybe you need to do it a different way, like grams to moles to moles to grams. But in this case, we've got a solubility problem. We've got 12.9 grams of lithium hydroxide. That 12.9 is attached to lithium hydroxide. The 100 is attached to water. And I go ahead and I plug that in my calculator by typing 50 times 12.9 divided by 100. And I get 6.45. Now, I've only got 2 sig figs here, so I only get 2 sig figs at the end. Remember, oftentimes when we have conversion factors, one of the numbers is exact, so we're going to treat this guy as exact, and the 12.9 is measured. So if we were limited by the 12.9, it would be 3 sig figs, but we're limited by this first one. So 6.5 grams of lithium hydroxide. Again, one of those cases where the number is not our answer. What did we just calculate? We calculated that given 50 grams of water, we can dissolve 6.5 grams of lithium hydroxide. That's what we just calculated. Now, we have to compare that to reality. We have 8.0 grams of lithium hydroxide. That's too much. Not all will dissolve. Not all. Not all will dissolve. And what do we call that? We call that saturated. And that's our answer. But again, we need that logic to show how did we get from this number up here to this conclusion of saturated. All right. So let's do another one where the numbers are getting a little harder. We've got 10.8 grams of calcium iodide to 18 milliliters of water. The solubility is 67.6 to every 100 grams. That one, you'd have to do a little math in your head to try to figure that one out. Doesn't matter what we start with. We can start with the calcium iodide. We can start with the water. If you notice something, though, we've got an issue here. All of a sudden, we stopped talking about grams of water, and now we're only talking about milliliters of water. What are we going to do there? Well, if you look at the solubility, it's got to be grams of water. So at some point, I've got to get those milliliters over to grams. How do I convert between grams and milliliters? You think to yourself, grams and milliliters, grams and milliliters, grams and milliliters. And hopefully, if you think long enough, you eventually come up with density. That's our relationship between grams and milliliters. Now, luckily for us, the density of water to 3 significant figures is 1 gram per milliliter. So 18 milliliters of H2O times 1.00 grams per 1 milliliter is 18 grams of H2O. And so we're good here. We actually don't need to change the number, but we did have to change the units. Right? Don't skip those kind of steps if you're doing stuff that requires showing your work. Don't skip that step. Actually show that you understood that milliliters and grams are not necessarily the same thing. The only reason they were the same here is because it was water with a density of 1. If I had ethanol, then you'd end up with a different answer because ethanol doesn't have a density of 1. All right, so now we've got that. We can start with either the solute or the solvent. Doesn't matter. Let's go ahead and start with the solute. We've got 10.8 grams of calcium iodide. And what we want to find is grams of water. We've got a conversion factor here. Grams of calcium iodide on the bottom, grams of water on the top. Goes like that. How do we get those numbers? Grams of one thing to grams of another. You should think about solubility. We go up here. We're given this information. 67.6 grams of calcium iodide. It's attached to calcium iodide. It stays attached to calcium iodide. 100 grams of water. I type that into my calculator. I've got 10.8 times 100 divided by 67.6. I get myself 15.976. What do I have? 3 sig figs here, 3 sig figs here. So I get 3 sig figs at the end, and it's 16.0 grams of water. What did I just calculate? I calculated that in order to dissolve 10.8 grams of calcium iodide, I need 16.0 grams of water That's still not my answer, because what's my answer? My answer is I have 18 grams of water, more than I need. And if I have more water, if I've got a bunch of extra water, what could I do? I could dissolve more calcium iodide. Right? A little extra is the same as a lot extra. Imagine I had an entire ocean full of water. Can I dissolve some more calcium iodide? Absolutely. And we call this an unsaturated solution because I could dissolve more if I wanted to. So those are our calculations for saturated and unsaturated solutions. We can start with either the solute or the solvent. We use the solubility as the conversion factor, and then we have to use a little bit of logic at the end. Here's an example for you to try. We've got the solubility of lead 2 acetate in water. It's 44.3 grams of lead 2 acetate per 100 grams of water. We're going to take 479 grams of lead 2 acetate added to 945 milliliters of water. How would you describe this solution? Again, great chance for you to pause, actually try it out. Just thinking about it, just looking at me doing it is so not the same thing. Actually stop, try it out, and then you can always start the video up again. Welcome back. Hope you had a good time solving the problem. What do you want to start with? Do you want to start with the solute or the solvent? Doesn't really matter. Let's start with the solute again. 44.3 grams of lead 2 acetate. Pretty complicated formula, pretty long word to write. Of lead 2 acetate, we're going to put a conversion factor in there. We're trying to get to grams of water. So grams of water goes on top. Grams of lead 2 acetate goes on the bottom. Where do I get those numbers? Grams of one thing, grams of another thing is solubility. And 479 grams of lead 2 acetate. So my 479 is attached to lead acetate. 479 and whoops. And you know, what did I do? Did I make a mistake? I did. I did make a mistake. Why? Because I started with my solubility. I didn't start with what I had. I started with my solubility. Does it happen? Absolutely. I've been teaching this class for years and it just happened to me. Is it going to happen to you? Absolutely. Don't tear your hair out over it, right? Mistakes happen. And I looked at it and I'm like, wait, I don't have my solubility number because I already used my solubility number. I'm confused. And so I said, oh, that's because I used the wrong number to begin with. And so I'm going to go ahead and correct myself. It's fine. That's what erasers are for. Okay. So what did I actually start with? I actually started with the 479 grams of lead 2 acetate. That's my reality. Reality always goes out here in these kind of problems. And theory always goes in here. It's not always true for all problems, but for the solubility problems, it's pretty true. Okay, so what's my theory? That's my solubility. I've got my 44.3 grams for every 100 grams of water. Now I can multiply that out. I've got 479 times 100 divided by 44.3. I got myself 3 sig figs. There we go. I'm like, that's not the number I expected. I get 1,080 grams of water with my 3 sig figs, not 108. Remember, we have to carry down that 0. So we get 1,080 grams of water. That's how much I need. I only have 945 milliliters. I don't have enough water, which means not all of it's going to dissolve, and I have a saturated solution. Again, you want to write down that logic if you were writing this down completely, but I just said it out loud for you guys. Couple more examples. Here we've got the solubility of potassium chloride is 34.4 grams for every 100 grams of water. How much water would need to dissolve 47.9 grams of potassium chloride? So this isn't a saturated unsaturated problem, but it's exactly the same problem we were just solving. We're starting with how much potassium chloride need, and we're trying to find is how much water. So we're going to start with the 47.9 grams of potassium chloride. We're going to put grams of potassium chloride down here. Now, the only thing we know is that to grams of water. Even though we want milliliters of water as our answer, we don't know how to go straight to milliliters of water because our solubility only does that, which tells us we probably have another step coming next. Grams of potassium chloride. What do I put down there? Remember, this is usually the theory. This is the solubility. And so I get 34.4 grams for every 100 grams. But now I need to get those grams of water into milliliters of water. But luckily for us, that's just density, 1 gram per 1 milliliter. So I typed that into my calculator. I got myself 47.9 times 100 divided by 34.4. And I get 139.244. I only got 3 sig figs in my thing, so I get 139 grams of water is how much water I need to dissolve 47.9 grams of potassium chloride. A quick question here. Would it be more or less soluble at 30 degrees Celsius? We're going to figure that out in the next video, is what happens to these solubilities as temperature changes. I think that's the end. Oh, one more. All right. The solubility of copper 2 fluoride is 0.075 grams for every 100 grams of water. How much copper 2 fluoride can be dissolved in 870 milliliters of water? Pause your video, try it out. All right. 1870. When you're working this out for me, show your work. I'm going to cheat because it's water, and only because it's water. I know that's 1870 grams of water because the density is 1, but you want to show that work if you're ever showing work to me. All right, so 1870 grams of water. I'm going to convert that, and I'm going to try to find grams of copper 2 fluoride that I need to do that. So grams of water has to go on the bottom here so it can cancel. Grams of copper 2 fluoride go up here, so I get them over here. Then I try to find those numbers. The numbers in that parentheses, grams of one thing, grams of another, is usually a solubility, and I get 0.075 grams for every 100 grams. I type that into my calculator, 1870 times 0.075 divided by 100, I get 1.4 grams. Why only 2 sig figs? Because this guy only has 2 sig figs. So I get 1.4 grams of copper 2 fluoride is how much I can dissolve in that much water. Thanks for watching. We learned how to figure out whether solutions are saturated, unsaturated, and we learned how to do a few calculations of how much water do I need if I want to dissolve this, or if I have this much water, how much can I dissolve? And we'll continue to use those units in future parts of the class. Thanks.